Hello, my mathematical friends. Today, we're going to kind of just keep going with what we did yesterday, which is focusing on solving systems, solving nonlinear systems, okay? Yesterday, our focus or our attention was on graphing. So we would put both equations into y1 and y2, and we would look for the intersection point. Or if by hand, we would graph each by hand and look for the intersection points. Okay, today we're going to shift our attention to solving algebraically. And really, you've done this in grade 10, you just haven't done it to this, this depth, okay? So if I said the words elimination and substitution to you, I would hope that that resonates a little bit from your time in grade 10. But if it doesn't, we are going to actually start with some grade 10 equations. And we're going to solve those guys, and then we're going to kind of build you up in this note to deal with then quadratics, a quadratic equation with a linear equation, or a quadratic equation with a quadratic equation. Okay, really the biggest difference between grade 10 and now, obviously the algebra is a little bit more in depth. But then you'll also often get two solutions, right? We saw that with graphing yesterday. So what will happen is when you get your two x values, you'll actually have to plug each of those x values back into an original equation and get out the y value, okay? But we'll deal with that as we go. If the first example kind of stresses you out, the first example is like doesn't really go beyond 10C. So if the first example stresses you out, I would encourage you to stop watching this video, go back and watch the 10C videos. There'll be one on substitution and one on elimination separately. So they'll go into a lot more detail for you. Go review those first and then come back and join me and carry on into the 20-1 material, okay? All right, awesome. So first of all, remember that we want to just throw some different vocabulary words at you from time to time that Alberta Ed will do so on your diploma. One of them is illustrate. So illustrate means make clear by giving an example. The form of the example will be specified in the question. So it may ask you for a word description, a sketch, or a diagram. Okay, so the first kind of question we're going to warm up with here is illustrate whether two parabola that both open downward have 1, 2, or no points of intersection using a sketch. Okay, so we want to do a sketch. I'm actually going to do a sketch and an example or a written explanation of my sketch. I would love it if you would pause me for a second and just see if you can come up with, is it possible to get 1? Is it possible to get 2? Is it possible to get nothing? Okay, so give me a pause and try that. Okay. So some of you may have said it's totally possible to get 1, and this is kind of the picture I'd want you to think about if we were getting one solution. Essentially, the parabola on the inside would have to be skinnier than the parabola on the outside, and then they'd have to share a common vertex. Okay, so yes, it is possible to get one solution. Was it possible to get 2 solutions? Well, think about this. If I took that skinnier parabola and I just moved it up, if I kept the fatter parabola exactly where it is, and I just moved the skinnier parabola up, you could see that I very well could get 2 solutions there, okay? So if the parabola on the inside is skinnier than the parabola on the outside and has a vertex above the wider parabola, then there'd be 2 points of intersection, okay? And I'm hoping now you can also see if I did the exact same thing, if I moved that purple skinny parabola down so that it was below the green parabola's vertex, then I would have no solution. So it is actually possible for me to get 1 solution, 2 solutions, or no solutions. And I've shown all 3 using a sketch, and I've also done an explanation. So the explanation for this one is if the parabola on the inside is skinnier than the parabola on the outside, and its vertex is below the wider parabola's vertex, then there would be no points of intersection, okay? Okay, so today we're going to tackle solving by substitution and by elimination, okay? And one is not better than the other. This isn't going to be another example where we often say, choose the most efficient one, okay? Certain ways we ask you the question it will line up that it's nicer to do by substitution or it's nicer to do by elimination, okay? But one isn't better than the other. And if you got the right answer, you'd never be marked wrong for not using the most efficient method, okay? I know we've talked about this before. The reason we're trying to encourage you to make sure you use the most efficient method is because the most efficient method is the quickest method, and we want to make sure you have enough time to write your test, okay? Okay, so we're going to start with a linear and a linear. Okay, I know both of these are lines because they both have an x and a y and no exponents. Solve the following system using the most effective method. Well, for elimination, I need one of my variables to have the same number there. For substitution, I need to be able to isolate one of my variables. Personally, this one I think lends itself better to substitution because I could take this bottom equation and I could just add 4x to both sides, and then I've got y all by itself. So I'm going to go ahead and do that. I'm going to add 4x to both sides. That gives me y equals 4x plus 5. Now, y equals 4x plus 5 is a statement that says anytime I see y, it is the same as 4x plus 5. So I can take that information to the other equation, that 2x minus 4y equals 8, and wherever I see a y, I can now replace that with what I know an equivalent expression is, 4x plus 5, okay? So I'm gonna put 4x plus 5 right here in for that y, okay? So I'm gonna write that equation as 2x minus 4 times y, but y is now 4x plus 5. Okay, equals 8. Now, the reason I wanted to do that is because now I'm looking at a equation that just has one variable, and I can solve that, right? So I'm gonna distribute my -4, so that'll be 2x minus 16x minus 20 equals 8. Okay, I'm just gonna get my head out of the way there. I'm just sorry, I stumbled there in my talking to you because I was wondering if my head was blocking that first line. Okay, so just so you can see that first line, where my head is in the recording and where my head ends up are not always the same thing. So 2x minus 16x minus 20 equals 8. Now I can go 2x minus 16x to get me -14x. I can add 20 to both sides to get rid of that. So that'll be -14x equals 28. And then I can divide both sides by -14 and get x equals 2. -2, sorry. Once I know that x equals -2, I'm going to take that guy. I'm going to go back to where I had left off, plug in -2 for my x value, and figure out the actual number for my y value. Okay, so I've arrowed back to where I had left off originally. I'm going to substitute x with -2. That's going to give me -8 plus 5. And so y is -3. So I have found the intersection point of this system. The solution will be bracket -2 comma -3. Remember that you always answer as a coordinate pair, just like that. Okay. All right. So this is the point in time where if I have completely stressed you out, this is a good time to stop and go back and look at solving by substitution and solving by elimination from the 10C videos, okay? Then, when you're ready, come on back and we'll keep going. Okay, so this next guy, again, it's still linear by linear. 2x plus 7y equals 24, and 3x minus 2y equals -4. Now, this is not set up as nicely to isolate for one variable, because no matter what I do, if I was to isolate for one variable, I would end up with fractions somewhere, okay? If I wanted to isolate for this y, I'd have to divide everything by -2. If I wanted to isolate for this x, I'd have to divide everything by 3. So I would say the more effective guy here would be elimination. Okay, so now I'm going to walk you through elimination. In order to do the process of elimination, you want to make one of these numbers, one of the numbers on the letters, to be the same. So either I want to eliminate x by making the coefficients of x the same on both, or I want to eliminate y by making the coefficients on y to be the same for both. Okay, I chose to eliminate x, and so I did that by multiplying the top guy by 3 and the bottom guy by 2. If I did that, I would end up with 6x for both of these equations. Okay, so communication is super important in math. So you'll notice I'm arrowing over to write new equations, but as I arrow over, I'm communicating what I'm doing. I'm communicating that I'm going to multiply the top guy by 3. I'm communicating that I'm going to multiply the bottom guy by 2. Okay, now I can't just do that to one term. I have to do that to every term. So the top function is now going to be 6x plus 21y equals 72. And then the bottom one, if I multiply all of that by 2, I'll have 6x minus 4y equals -8. So in this first step, again, I'm going to hide my head here for a second just to make sure you can see that. Okay, in this first step then, what I need to do is I need to eliminate the x's. And I'm wondering to myself, would I want to add or subtract in order to eliminate? Because the signs are the same right now, I would want to subtract. So if I'm going to subtract my x's, I subtract each item along the columns that you kind of see there, okay? So I'm going to say to my reader that I'm subtracting. 6x minus 6x is gone, that's 0, right? So that was the whole purpose. 21 minus -4 would be 25, and 72 minus -8 would be 80. Okay, so now I have a little algebraic equation that says 25y equals 80. I can divide both sides by 25 and then reduce that fraction. Okay, so when I do that, I end up with y being 16/5. It is okay to have fractional answers. Nothing wrong with that. Don't put them as decimals, leave them as fractions. Okay, we want everything to be left as exact value unless the question explicitly tells you to round. Okay, now that I know y is 16/5, I want to go back to one of my original equations. Doesn't matter which one. You can choose the first one, choose the second one, but you're going to plug in 16/5 for y and solve for x. Okay, whoops, sorry. Okay, so I just plugged it into the first guy that I saw, 2x plus 7. I'm substituting my y with 16/5, and then that equals 24. Okay, again, don't let the fractions freak you out. I'm not going to take your calculator away on a question like this, but if you wanted to do it without a calculator, you know that 7 is 7/1, and you'd multiply the tops and multiply the bottoms. So you're really just looking at 7 times 16 there, which is 112. Okay, so that gives me 2x plus 112/5 equals 24. Now, to get x by itself, I would want to subtract 112/5 from both sides. Okay, so if you wanted to do it by hand, you would want 24 to be a fraction over 5, right? So you just take 24 and multiply it by 5, so you could write it as a fraction over 5, and then subtract 112. In your calculator, you can just go 24 minus 112 divided by 5, and then put that as a fraction. Whatever works for you, okay? So that's going to give you 8/5. Then you're not quite done because you don't have x by itself yet. You'd have to divide by 2. 8/5 divided by 2 is 4/5. Okay, so for this guy, my solution is the coordinate point that I just found, right? So bracket 4/5, comma 16/5. Okay, 4/5, comma 16/5. Okay, so that was a quick review of elimination. Now we're going to look at a quadratic with a linear system, okay? A system that is a quadratic and a linear. Now, the most effective method, again, personally for me, I kind of see this -y as pretty darn friendly, because if I moved that over here, it would be +y. And then I actually would be ready to do substitution, right? Because I'd have a statement that reads y equals x squared plus 5x plus 4. And I could just then replace it for this y right here. Okay, so that's exactly what I'm going to do. I've rearranged the top guy so that it says y equals x squared plus 5x plus 4. That means anytime I see a y, I can replace that y with x squared plus 5x plus 4. That's why this process is called substitution, because I'm substituting a letter with a expression that I know is the same thing or equals the same amount. Okay, so I'm going to take this 2x plus y plus 8, and I'm going to substitute my y with the x squared plus 5x plus 4. Okay, now just like I did with the first substitution example, I'm just down to a one variable item to solve. The difference between now and like 2 examples ago, is that when I clean this up, I have an x squared and I have an x, which means I have a quadratic to solve. And so I'm going to have to look at factoring this. Okay, so this is going to be x squared. I'm going to have 7x and I'm going to have 12 when I combine all my like terms. I'm going to factor that into x plus 3 and x plus 4. Okay, and now I have the zero product principle. So x plus 3 could be 0, which means x is negative 3. Or x plus 4 could be 0, which means x is negative 4. Okay, so now that I have my 2x values, this is important because this is slightly new in your thought process, okay? Lots of kids want to say you're done now because you've got 2 answers and you can just move on. But we need the points of intersection. These are only the x values of 2 separate points of intersection. So now we have to get each y value that goes with these separate x values, okay? So I'm going to plug in negative 3 to one of my original equations. That's going to give me negative 6 plus y plus 8. So that'll be y plus 2 equals 0. And then I'll bring that 2 over. So y will equal negative 2. So this is now going to give me the point negative 3 comma negative 2. The original x value was negative 3 and I got out negative 2. So that's 1 point of intersection, bracket negative 3 comma negative 2. I now need to do that again, only using x equals negative 4. Okay, so I'm going to plug in negative 4. 2 times negative 4 is negative 8. 8 plus negative 8 is 0. So I end up with a statement that reads y equals 0. And so that's the point, negative 4 comma 0. Okay, negative 4 comma 0. So there are 2 intersection points. There are 2 solutions to this system. And they are negative 3 comma negative 2, as well as negative 4 comma 0. Okay, so graphically, if I was to graph both of those functions, those are the 2 points where the functions would overlap each other. Algebraically, what I just found out is these are 2 separate values for x and for y that would satisfy both equations at the same time, right? That's what a solution to a system refers to. I could plug in negative 3 for x and negative 2 for y and get a true statement in both of them. Or I could plug in negative 4 for x and 0 for y and get out a true statement for both of them. Okay. All right, good job. Now let's try this guy. Again, the most effective way. Well, I could move the y's over here and move this y over here so that they both say y equals, and then I could set them equal to each other. That would be substitution again. Okay, but the way this is all set up, and given that y is already on top of y and that they're the same magnitude, I just want to eliminate them. I could just subtract all of these little columns here and I would have no y there. I'd just be left with an equation that involves x and try and solve for that. Okay, so I'm going to subtract. When I do that, I get this is 1 minus 2, so that's negative x squared. This is negative 3 minus negative 8, so that gives me positive 5x. My y's are gone. Negative y minus negative y is nothing. And then 3 minus 9 is negative 6. Okay, I'm going to now try to factor that. But before I do, just as a word of caution, the one difference between, say, grade 10 material and 20-1 material now, when I go to do substitution or when I go to do elimination, it's still always y that I'm either trying to isolate or eliminate. Okay, because I want to be left with the x squared and the x so that I have a quadratic that I can factor or head to the quadratic formula or complete the square or whatever I need to do there. Okay. Okay, so we're going to go back to the negative x squared plus 5x minus 6 that you see on your screen. I'm going to go factor that, but I don't like to factor when there's a negative on the x squared. It's way easier when that's positive to just see. It's just a better visual. So let's multiply everything by negative 1. That's going to give me x squared minus 5x plus 6. Now I'm looking for 2 numbers that multiply together to give you 6 and add together to give you negative 5. That would be negative 2 and negative 3. And so now I'm at the zero product principle. Again, I know I was harping on this the other day, but just make sure every sentence you write here needs to say equal 0, because if it doesn't equal 0, there's no reason for you to be able to use the zero product principle, right? I need to see a product that equals 0 in order to use the zero product principle. Okay, so either x minus 2 could be 0. and that would mean x is 2, or x minus 3 could be 0, and that would mean x is 3. Okay. All right, so those are my original x values of 2 separate points. We don't put those together. These are 2 separate points. One x value is 2, the other x value is 3. I need to now go and get the corresponding y values for each of those x values, okay? So it doesn't matter which equation I pick, I just happen to pick the first one, and I brought that y over, so I just added y to both sides, okay? Let me get rid of my head here so you can see what I'm talking about. And I'm plugging in 2 for x, so I've got x squared minus 3x plus 3. Okay, that gives me 4 minus 6 plus 3, which means y is 1. So that concludes the point 2, 1. Okay, 2, 1. Now I'm going to do it again, but this time I'm going to replace x with 3. Okay, so now I have 3 squared, which is 9, minus 3 times 3, which is 9, plus 3. That's just going to give me 3. And so that's the point 3, 3. So there are 2 solutions. There are 2 points of intersection for this system. One of them is at 2, 1, and one of them is at 3, 3. Okay. Good job, guys. All right. These sorts of questions are fun. Determine a possible value for q that would result in a linear quadratic system, y equals x squared plus 3x plus 1, and y equals negative x plus q, having only one intersection point, and then justify graphically. Okay, I am going to take my head away for a second just to talk about the fact that I want you to first notice if this is a system, I've got this equation and I've got this equation, but they already both say y equals. Okay, so when they already both say y equals, I can just take this guy and I'm going to plug it in for the y value here. Okay, and then I've got a statement that just has negative x, or sorry, just has x involved. Doesn't have to be negative x. Not quite sure why I said that. Actually, I'll tell you why I said that. It's because I'm trying to find the button to put my head back. There's my head. Okay, so that would leave me with this statement here. X squared plus 3x plus 1 equals negative x plus q. Okay, so now I want to solve that. So I want to bring everything over to one side so that it equals 0. So that's going to give me x squared plus 4x and plus 1 minus q. Okay, x squared plus 4x plus 1 minus q. Now, question for you. I'm left with a quadratic here that equals 0. I'm trying to solve a quadratic, and I want the solution to only be one solution. If I only want one solution to a quadratic, what should that be screaming out at you right now? You're all home screaming, the discriminant, right? Yeah, humor me. Okay, so the discriminant, again, just as a reminder, is b squared minus 4ac. If I want one solution, the discriminant has to equal 0. Okay, so I'm going to say b squared minus 4ac has to give me 0. Now, my a value is 1. My b value is 4, and my c value is 1 minus q. Okay, so I'm going to plug that in for a, b, and c below. And I get the following. So 4 squared is 16. Negative 4 times 1 is just negative 4, and then I have to distribute that negative 4 into those two terms. Okay, just let me draw that for you. So it'll be like that. So that'll give me negative 4 and plus 4q. Okay, so 16 minus 4 plus 4q equals 0. 16 minus 4 is 12. I'll bring that to the other side. So I get 4q equals negative 12, which means q has to be negative 3. Okay, so what we're saying is if that q value is negative 3, I will create a system where there'll only be one solution. Okay, so now it says justify your answer graphically. So I am now going to show you these two equations where y1 is x squared plus 3x plus 1. y2 is negative x minus 3 because my q value is negative 3. Okay, and then when I show you those graphs, you can see there is only one intersection point of that system. It happens to be at negative 2, negative 1, but that wasn't what the question was asking. They were just asking what's the value of q that would make just 1. Okay, if you think about that red line that I've drawn there, if I move that up at all, there would be two solutions. If I moved it down at all, there would be no solutions, right? That is the sweet spot for this particular system that would make it just one solution. So Q would have to be -3, okay? Those are cute little test questions. So that's something you want to make sure you understand really, really well. Okay, so let's kind of do another Q question together. This one is determine all the values of Q for which the system y equals x squared plus 3 and y equals Q has. So for those of you at home just needing to see that question, I'll hide for a sec. Y equals x squared plus 3 and y equals Q is my system, okay? So if I want exactly one solution and if I want exactly no solutions and if I want two solutions is what I'm looking for, okay? Again, I'm going to set it up the same way. These both say y equals already, so I'm just going to set them equal to each other. Okay, and that's going to give me x squared plus 3x equals q. I'm just going to hide myself again for a second, just to make sure you can see that. Okay, I'm going to bring the q over, so I'd have x squared plus 3 minus q equals 0. Now, I'm going to start the conversation with just the exactly one solution. Exactly one solution means the discriminant has to be 0. If I'm looking for the discriminant, my a value is 1, my b value is 0, there is no x term here, and my c value is 3 minus q. Okay, so I'm going to plug those items into the discriminant, and I'm going to solve. So I've got -4 again, that gets distributed to the 3 and to the negative q, so that'll give me -12 plus 4q equals 0. Then I'll add 12 to both sides and divide by 4. Q is 3. Okay, now that is the answer for exactly one solution. Okay, if I want exactly no solutions, I don't know why I keep saying exactly there. If I want no solutions, I essentially just need to bring that down, right? So think of it this way. If I want no solutions, I just want to switch ink color here for a sec. If I want no solutions, the discriminant would have had to have been less than 0, right? So it would be this whole same conversation, except now we would say Q is less than 3. Okay, so Q is less than 3. And likewise for the other guy, if I wanted two solutions, I would just switch all that to greater than, and so Q would have to be greater than 3. So these are my three kind of possibilities. They all center around 3. If Q is 3, I will have exactly one solution. If Q is anywhere less than 3, I will have nothing, no solutions. And if Q is greater than 3, I will have two solutions. Now, I have graphed that for you here. Okay, so Q equals 3, I put in as y2. Q is less than 3, I put in as y3, and Q is greater than 3, I put in as y4, with the x squared plus 3 as y1. So when I show you this graph, if all of this worked out, what you should see is the red line will intersect with the blue graph once. The green line will never intersect with the blue graph, and the pink line will intersect twice. And you can see that that's exactly what happened. Okay, awesome. Okay, last question for today. The price C in dollars per share of a high-tech stock has fluctuated over a 12-year period according to the equation C equals 14 plus 12x minus x squared, where x is the time in years. The price C in dollars per share of a second high-tech stock has shown a steady increase during the same time period according to its relationship, which is C equals -6 plus 16x minus x squared. For what values or values are the two stock prices the same? Okay, well, the first thing I want you to see is I've already written both of these equations in terms of C. So this lends itself very, very easily to just solve by substitution. I'm going to stick this guy in for this C, okay, and I'll just get an equation that says -6 plus 16x minus x squared equals 14 plus 12x minus x squared, or vice versa, right? It doesn't matter who's on what side of the equal sign. Okay, and so that's what you're looking at here. And now I can add x squared to both sides, and that actually is going to eliminate all my x squares. It won't, I won't have any. I'm going to subtract 12x from both sides, and I'm going to add 6 to both sides. So that gives me a statement that reads 20 equals 4x. Okay, and I just have to divide by 4, so x equals 5. Always when you're asked a real life context question, make sure you answer the question within the context. So the two stocks are priced the same at the 5-year mark. Okay, the two stocks are the same at the 5-year mark. All right, good stuff. So that's where I'm going to leave you today. We're going to just do a very quick, in your book, you have these steps for those of you who like steps. Here are the steps for substitution that we covered today. Number 1, you'll isolate an easy variable, then substitute the new expression into the other equation, solve that equation, because now there's only one variable there. And then once you have a number for that one variable, go back to one of the original equations and plug it in so that you can get the value of the other variable. Okay. For elimination, make sure the equations are in the same form. So like x squares on top of x squares, x on top of x, y on top of y, number on top of numbers, that sort of thing. Make the coefficients of the same variable in both equations the same in magnitude. So it doesn't matter the sign. I could have a 4 and a 4, or I could have a 4 and a negative 4. Okay. Add or subtract the equations to eliminate a variable. Use algebra to solve for that one that's left. And then once you have him, just like in substitution, put him back into one of the original and figure out the other guy. Okay. All right, so there is your mission. Give yourself lots of processing time, give yourself lots of practicing time. Remember, the way you're successful in 20-1 is to go over this material, and not just to try and memorize a process, but to understand what's happening. If you can understand what's happening, you're going to have a much deeper level of success with this. Okay, this is not about memorizing, it's about understanding. And on that note, if you don't understand, make sure you're connecting with me. Okay, that's what I'm here for. All right, guys, take care. We'll see you soon.